What happens at a synapse? When you think about a synapse, it can include some kind of target, the synaptic cleft, and an axonal terminal. So let's use a blue pen to label these. This represents the axonal terminal. This space between the axonal terminal and whatever the target is called the synaptic cleft. And this right here represents the postsynaptic membrane. The target. So it could either be a muscle cell, so a skeletal muscle, or a smooth muscle, or a cardiac muscle cell, or it could be the dendrite of another neuron. So if you think about some locations, where would you imagine that it would be an axon terminal with another dendrite? Like the brain, right? Is a good place where you would find that, and the spinal cord. And then going on to a skeletal muscle cell, or a cardiac muscle cell, or a smooth muscle, you'd be looking in the peripheral nervous system, so the PNS. So kind of get that big picture in mind. All right, now use your black pen again and remind yourself by writing here that the action potential is coming in this direction. And when it arrives at the axon terminal, instead of depolarizing the axon terminal by allowing sodium to rush in, instead calcium channels open. So that's the first thing that we'll put. You can get your blue pen again. The first step that I'll describe to you is that the action potential reaches the axon terminal and causes calcium channels to open. Calcium will predictably rush in because calcium is more concentrated outside of the cell than inside. So we can put the calcium outside of the cell, and it is going to rush in, and that's step 1. Okay, now you can use your pink highlighter and make a few synaptic vesicles here. And then put some neurotransmitters inside of those with a green highlighter. Like so. And then let's label them. Label them synaptic vesicles. Contain neurotransmitters. And you can highlight or somehow make a note that the neurotransmitters are the green dots. And what are some of those possible neurotransmitters? Use a green pen. Move your paper up a little bit. They could be acetylcholine. That's important in the brain, and it also is at every neuromuscular junction, and it is the mediator of parasympathetic function. So, it's common in the brain, in the central nervous system. It's common in the voluntary motor output, which is skeletal muscles, right? It's the mediator of what we, at the neuromuscular junction. And it is responsible for parasympathetic effects, such as slowing your heart down, constricting your pupil, and activating your GI muscles, all of those kind of actions. So very common. So if you're going to look over here, if it is a skeletal muscle cell, then we're talking acetylcholine. Another common neurotransmitter is norepinephrine. It's also common in the brain, and it is the mediator of sympathetic functions. So it's making your heart go faster, dilating your pupil, a bunch of other important jobs like that in fight or flight. And then in the brain, we could be looking at glutamate, or serotonin, or GABA, or dopamine. So these are various other important neurotransmitters, mostly CNS. But interestingly, you find a lot of these kinds of neurotransmitters in your gut too. So it really is true that what you eat can affect the levels of even like your mood neurotransmitters, things like that. Okay, so back to our story of what's happening. The action potential gets to the axon terminal and the arrival allows calcium channels to open, calcium predictably rushes in, and then that effect is to cause exocytosis of the synaptic vesicles. So I'm going to use a purple pen, write number 2 on here. Calcium causes exocytosis of synaptic vesicles. So the neurotransmitters are going to get dumped into the cleft. So you can use your purple highlighter and show that exocytosis is occurring. That's step number 2. Oh, can't really see what I did there, did you? So I highlighted in purple like this, put a number 2 on there. Calcium triggers exocytosis of synaptic vesicles. And number 1 was allowing the action potentials. The action potentials allows calcium to rush in. So that's step number 1. And then this is step number 2. And then use your pink highlighter to show that merging. Exocytosis means that these lipid sacs, they're made of phospholipids, merge with the phospholipid membrane and allow the neurotransmitters to get dumped out. And then that brings us right to step number 3. The neurotransmitters, I'm going to use a pink pen for step number 3. The NTs diffuse across the cleft and bind receptors on the target. So you can show the neurotransmitters binding because they diffused across, and use your pink pen to put a big number 3 here, showing its binding. And now we'll talk about receptors a little bit. Use an orange highlighter, color those receptors. The receptors are named according to what kind of neurotransmitter they bind. So, accordingly, acetylcholine would bind to cholinergic receptor, because you hear the choline in there, so they bind to cholinergic. So ACH binds to cholinergic receptors. Norepinephrine binds to adrenergic receptors. Now that name doesn't jump right out at you, right? Like choline is in the word acetylcholine, so cholinergic. Norepinephrine, another name for it in the old days, was noradrenaline. It gets its name because it comes out of the adrenal gland too during fight or flight. So based on that old name, then the receptors are called adrenergic receptors. And then glutamate would bind to glutaminergic or something like that. And so that, or dopamine binds to dopaminergic receptors, etc. Now, the receptor types are what are going to determine what happens. So let's put pink again down here. Or actually, let's use orange, right? Because we're talking about receptors in orange. So receptors determine the effect on the target. So let's think of some possibilities of what could happen. If this were, if the target is a skeletal muscle, then what would happen is ACH would bind to cholinergic receptors, and specifically a type of cholinergic receptor called a nicotinic. And yes, that is, nicotine is one of the chemicals that they've used when they're studying those. So nicotinic cholinergic receptors, and causes sodium channels to open on the muscle fiber. Ta-da! Contraction. Well, actually, don't put that yet. Depolarization. Followed by contraction. So a skeletal muscle can be electrically excited by acetylcholine, and then that electrical excitement ultimately causes the muscle to contract or change length. And that's something we'll get more into the mechanics of that later on in the quarter. Okay, so what if this were heart muscle? In that case, acetylcholine and norepinephrine can bind. But let's say it was acetylcholine, and it's going to bind to a different type of receptor called a muscarinic cholinergic receptor. Opens potassium channels on the cardiac muscle cell. Now what do you think is going to happen? If potassium channels open, then which way will potassium go? It will go out, right? And if you think about the previous page of your notes about action potentials, if potassium leaves the cell, what happens to the membrane potential? You have positive going away, so you end up more negative, right? So calcium or potassium leaves and hyperpolarizes the cell. This is going to make fewer contractions in the cardiac muscle, and the heart will slow down. So the same neurotransmitter, acetylcholine, on skeletal muscle causes sodium channels to open. Sodium rushes in, you get depolarization followed by contraction. It's a stimulatory effect. But if acetylcholine binds to muscarinic cholinergic receptors on the heart muscle, now it opens potassium channels which makes or allows potassium to leave, and now you have actually an inhibition of activity.